Hello, good morning, and welcome back. Today, we are going to discuss how to design a predictor for linear regression model. This is extremely important. After knowing all the bits and pieces of the tools and techniques and basic principles of linear regression model, now I would like to tell you the design process of a predictor. Although I am taking the example of a linear regression model only, but same design principle will be valid for all other machine learning based model development. That's why it is very important. Please try to understand and concentrate. As you know, for designing any machine learning model, what is the raw material? It is the data, real data in that particular domain. Let it be housing price prediction, or it could be your stock market prediction, or anything, right? You need data from that domain, and data should be real. Past data should be real data, right? When uh, with which you will actually develop your model. First thing what you need to do actually is to clean and explore the data. This is very important, that how to clean the data and how to explore the data. Hmm. Cleaning means if the data is large and in a tabular form, you have collected it, it could happen that in the table, some of the data may be missing, or there could be a duplicate entry. So all these things should be corrected during data cleaning process. Take the example, simple example I am giving. Suppose in a row you have entry like this, and in a particular column, entry is missing. So what you can do, you can see the trend of the data and you can just fill that 3, 6, and could be 9, 12. But this kind of simple pattern understanding may not be always possible. So you can um, extrapolate the data. For example, if you have um, 6 or interpolate the data, 6 plus 12 divided by 2 equals to 9. So this is more general. Then you can put 9 instead of missing data. Okay. So in this way, you can also extrapolate sometimes 3, 6, 9. Then what could be the next data? Again, take the same um, principle, that if possible, you try to explore any rhythm within the data, and logically it should follow. If it is 3, 6, 9, then could be 12. If not, then you could extrapolate the data. Okay, so that is what is known as, is a part of data cleaning process. Then you try to analyze um, the data to understand its distribution, trend, and correlations. Then you can visualize using the tools like scatter plot, histogram, correlation matrix. So all this tool will help you to visualize the data. Um, if dimensionality of the data is not very high, normally they are not for practical purposes. And then at the end, you will get um, well understood, well explored data. Once you explore the data, then there is another process known as feature engineering. What it is, you see, suppose you have collected some data, again, housing price, for example, the price of the house, corresponding to the floor area. X is the floor area, mm, floor area, and this is the corresponding price. But you have collected the data, and through visualization, you realize the data trend is not linear. Okay. So what you can do, you can actually, uh, I'm taking a simple example to illustrate the fact. Instead of doing a predictor like this, linear predictor, as you see, the collected data is not linear. So what you can do, you can complicate a bit by adding a new feature. You have a feature X, no other collected feature. So this is called engineered feature. So from X, you squared it, it became X squared. Similarly, if you still think the distribution of data is following some higher order polynomial, you can uh, create or engineer another feature. So remember, X, X square, X cube, they are all different features. And from X, you engineered feature mm, so as to fit your uh, data which you have collected and analyzed. Okay. And then, as I have already discussed in my earlier lecture, while discussing how to monitor the health of the gradient descent algorithm, there I have told you that why feature scaling is needed, normalization features, why they are needed. If you mm, um, if you don't remember, please go back and listen that video. The feature scaling here is very, very important to do. So all this, when done, actual design process now you can follow. So you are ready to actually design your predictor. So what is my objective? Build predictor so that prediction error should be minimum. That's why we need to evaluate, build and evaluate whether you, whatever you have designed, evaluation, I will talk about evaluation analysis also here, how to evaluate, and but it is needed. Uh, After building, you evaluate how good or bad your model is, and then if you are satisfied, then only you freeze the design. So let us um, let us suppose that we decide to build the model using elastic net regularizer. Again, in my earlier class, I talked about L1 regularizer, L2 regularizer, that means lasso, ridge, and elastic net regularizer, which is a combination of lasso and ridge. So if you don't remember, please listen to my earlier video before moving forward. First of all, you need to design your objective function, which is actually JW equals to um, your predicted parameter, actual parameter. This is mean square error. And if required, you can always put this mathematical convenience. M is the number of sample. And since you will run gradient descent algorithm, so you can put always 2 so that derivative will simplify the um, evaluation process. And then plus, you see, plus you have added, we have added here a regularizer term, elastic net regularizer. You see what it is. So lambda is called overall regularization strength, or sometimes we also call it penalty parameter. So lambda times, there is another parameter alpha, summation of j equals to 1 to n mod jw. So what it is, you know, by understanding, by watching my earlier video, you know, this is nothing but L1 regularizer or lasso regularizer. So you have added lasso regularizer with a term alpha plus. So lambda is penalty term, again keeping same. You have added 1 minus alpha times ridge regularizer. This is nothing but ridge regularizer or L2 regularizer. You remember who proposed this? Tikhanov, Professor Tikhanov. Okay. So these two regularizer, you see what you have done. Hmm. Suppose now, uh, so alpha is a value actually, and that we do in our design process. Alpha actually lies between 0 and 1. So if alpha equal to 0, that means you have not um, incorporated lasso regularization. Entirely your objective function uh, with ridge regularization um, is there for further processing. If alpha equals to 1, then of course this is gone. Uh, This regularizer is gone. So only remaining regularizer is lasso regularizer. So by playing trick with the value of alpha, we can keep both the regularizer with some weightage. Okay, so this is a control what you have between lasso and ridge regularization. Okay, so now let us take an example and how this regularization value will be determined. They will be determined through um, through the design process validation. Okay, so we have talked about what validation is in my earlier lecture. So if now you have original data set, clean and feature engineered, and then you divide the data set into two parts, training set, testing set. Normally, as I told you that 80% you can keep for training, remaining 20% you can keep it for testing. Testing means you will have to evaluate, right? And we will talk about the evaluation metric. It could be 70% also, 70, 30. So this is normal practice. So you have clean data and then you have divided it into training and testing part. And within training, just you make another set. So 80% of 80, say, for example, you have kept 80% of the total data. So out of 100 data, for example, 80 data is for training, 20 is for uh, testing. Then 80% of 80, that means 64, right? 64 data you keep for training, actual training, and the remaining 16 you keep for validation. Validation is similar to testing, but there is a difference. As you know, I have talked earlier. So this is an example of k-fold cross validation. Once you segregate training set and validation set, and then assigning that your lasso and bridge regularizer, you try figure out, and suppose you have given some values, say we have decided this should be 0.5 and then alpha should be 0.3. Then the lasso regularizer penalty contribution will be, so L1 or lasso penalty contribution, tell me, will be, just see, uh, this multiplied by this is lasso's contribution, will be 0.15. So what will be L2 or ridge penalty contribution? Here you see that 0.5, 1 minus 0.3, right, equals to 0.5, 0.7, 0.7. Actually, here it is divided by 2. Okay, so this 2, because you have seen that this could be actually well used for syncing the parameters. You can make it actually a 2 here, uh, compensate for that. So I'm sorry, there it should be corrected here. Mm. The 0.5 equal to 0.35 divided by 2 equals to 0.175, right? So the contribution with your parameter selection like this, that means your contribution from lasso is, you have decided that, okay, I will rely on lasso, which has the capability of completely annihilating some features. And Ridge has the capability of shrinking the parameter, as you know. So if you want very parse, so this is how actually sparsity in the feature space you can control that, whether at what weightage I should annihilate some of the features, what with what weightage I should shrink the parameters, okay, and later on decide its influence. So that's why that's how actually it can be done. So here is a hands-on example which tells you that by selecting lambda equals to this and this, you have ended up in almost equally relying on both the regularizer, and that may be good. Good or bad, then you will also have to again do cross validation. So, and you see, now we are coming here. Suppose you have selected some values and then designing with k-fold cross validation. So here 64, here remaining 16 you have taken, and then with that objective function, you have ended up in, this is actually error, what we call a root mean square error. Okay, and I will talk about that. Or it may be R square error. So normally we calculate, this is, suppose root means square error. That means, so whatever you have, objective function is nothing but what? Actually error function, no? This is nothing but error function. And if you do this, this is called root mean square error function. You can uh, consider two or not two, but it hardly matters. Okay. So, so you can. This is very good actually, because this is one of the good metric for evaluating your how good or bad your design is. So if you have designed in this process, I have not yet completed. Okay, let me complete first, and then we'll come. So you are collecting, say, this kind of error. Okay, always. And then this validation, what is validation? I have told you that validation set in the next iteration, they will be actually training set, and some other, you see, this validation set is now a training set. And I have slided some other 16, we have decided that they could be our validation, will be used for validation purpose. For example, exactly for determining error purpose. So that's why training earlier validation set will be our training set. Like that, you collect all the iteration 1, 2, 3, 4. This is k value is 4. K value could be more if you want, because this is a design. Your and others may vary. Okay. And suppose you have produced a model, and here it is very important that you are always getting error at the evaluation, right? Evaluation. So you can see that what um, um, uh, set of uh, lambda or alpha has created less number of error. So it's a tedious process, right? For one set of alpha and lambda, you will have to see error. Then another lambda and alpha, you will have to do the cross validation and all kind of thing. Okay. And once you are satisfied, then you can go for final testing. So your model is now created, and then you evaluate it, final evaluation of, with the test set. And remember, validation set, while you are using as a test, they are within the training set, right? And they are completely separate from the training set. So your actual strength of your model will be tested using test set. Again, you need to calculate RMS, some metric which can give you the minimum error, okay? How much error you are getting, and what is the RMS value. So if it is not within limit, then you can again have to come back, and maybe the entire this you need to change, incorporating another feature engineering, incorporating more feature, and then regularize. So all kind of, but actual process is actually this. Now let us discuss or inform you some of the metric like RMS is one of them. Another is R square, you know. So these are the two metric which normally we use. Here I have not give it two. You can eliminate that. Okay. Relatively, the root mean square error will be the similar. Okay. So this is root mean square error heavily used. So if a model has RMS value low, okay, compared to other model, then that model is better one. Another popular model evaluation metric is called R square. So it actually, you see what it is doing, it is calculating, it is making a proportion, proportionate uh, explanation it is giving that this is your predicted value, this is your actual value. So this is the error relative to what is the actual predicted actual value. Okay, that is dependent value in case of housing price. This is the price of the house, and this is the mean price of all the house. So this is basically the error is normalized uh, with respect to this to term. That means actual minus mean. This is very well-known technique actually. You are subtracting mean from the data to normalize the parameter R square, which actually trying to assess the goodness of the fit. Okay. It indicates actually, it is indicating how well the model explain the variability of the target variable, you know, and variability of the target variable, which has been created by dependent variable only, right? You have dependent variable, you have designed your W and X actually are the features, and they, based on your design, this is manifested. If this design is bad, then this will be more. And what will happen? This is constant for a data set, okay? Only for use for normalization. And then what will happen if this is more, the error is more, then this value R square value will be less, less and less, right? So now tell me if hypothetically, okay, if you have designed a predictor keeping all the data points here, then of course R square value will be 1, eh, which is not good, of course, the 100%. And is a overfitting problem. And if your data is like this, everywhere data is this, but you have highly biased, so that will be reflected when you calculate this parameter. Say it is very low. Normally it is calculated as percentage because this is actually is a proportion, right? Factor. So if suppose 100% R square value is a bad design, then say very low value also 5% also bad design because this is highly biased, it is uh, overfitted, this is underfitted. So normally R square value, if it is lying between 70 to 85%, again, I am telling normally because designing a machine learning model depends on your experience, like any other design, right? You only know the tools, techniques, and then I am telling all this behind the scene story. Then you will be able to actually handle the stuff, and maybe if you have patience, if you have good understanding, you will be a good designer. That's why I'm telling 70 to 85%, not 85% or 75%. It's not a mathematical calculation only, it is a design. So am I clear? So today you have learned uh, interesting thing how to design some topic about how to design a machine learning model, taking a specific example of um, uh, linear regression model, although the same design principle, iteratively, painstaking, with patience, you will have to come out with a good design, and you will have to make the design stand on the evaluation metric like root mean square error or R squared. These are the metric actually. And if you are satisfied, then you lock the design and sell the product. So you see, this kind of machine learning models are always everywhere almost. While we discuss in my last class um, about the applications of linear regression model, then you will see how versatile its use is. With this, I conclude. And if you have any problem, now I have given you a very well designed data set, and I have asked you to clean the data. So all the process which I have discussed today, you will have to practice using Boston housing price data. Okay, and um, submit the assignments. That will help you completely digest the design process. Wish you good luck. Bye bye.